To help explain the operation of the four-stroke engine cycle, we're going to use a representation of an engine. If we were to assemble this engine, we would start with the block and cylinder. The block is the foundation of the engine, and the cylinder forms the walls of the combustion chamber. We are now connecting the rings to the piston that form the seal between the piston and cylinder wall. The connecting rod is connected to the piston by a wrist pin, and the assembly becomes the movable floor of the combustion chamber. The movement of the piston up and down in the cylinder is defined as reciprocating motion. Assembling the crankshaft takes place next. The connecting rod attaches to the connecting rod crankshaft journal. The main bearing crankshaft journals attach to the cylinder block. The crankshaft changes the piston assembly's reciprocating motion to rotary motion. The flywheel bolts to the transmission end of the crankshaft. It is heavy and provides the momentum to continue the rotation during the time the crankshaft is not receiving power from a piston. The cylinder head forms the roof and completes the combustion chamber. The intake valve, when open, allows the air-fuel mixture to enter the combustion chamber. The exhaust valve, when open, allows the exhaust gases to exit the combustion chamber. When the valves are not held open, the springs pull the valves closed to provide a seal. The camshaft opens the valves using leverage provided by the camshaft lobes. It attaches to the top of the cylinder head, and rocker arms transfer the leverage from the camshaft lobes to force the valve open against spring pressure. The timing belt and sprockets are used to match or time the piston movement with the valve movement. The crankshaft gear is exactly half the size of the camshaft gear. This causes the camshaft to be driven at half the speed of the crankshaft. In other words, the crankshaft rotates 2 complete revolutions for every 1 revolution of the camshaft. The rotary motion from the crankshaft drives the timing belt and sprockets to rotate the camshaft. The spark plug is used to ignite the air-fuel mixture and attaches to the top of the cylinder head with its electrode extending into the combustion chamber. The intake manifold is used to deliver air to the combustion chamber through the intake valve. The throttle plate or valve is controlled by the driver and regulates airflow to the combustion chamber. Airflow is minimum at idle, medium airflow at half throttle, and maximum airflow at wide open throttle. The injector delivers the precise amount of fuel to mix with the air in the combustion chamber. The amount of time the injector is held open regulates that amount of fuel. The injector is located in the cylinder head intake port near the intake valve. The exhaust manifold provides the passageway to the exhaust system for the burnt gases leaving through the exhaust valve. The virtual engine is now ready to demonstrate the 4 stroke cycles of an internal combustion engine. An engine is identified as a 4-stroke cycle engine because each cycle of the engine takes 4 strokes to produce the force that rotates the crankshaft. The 4 strokes are intake, compression, power, and exhaust. During the intake stroke, the intake valve is open and the air-fuel mixture is drawn into the combustion chamber as the piston moves from top dead center to bottom dead center. On the compression stroke, the intake and exhaust valves are closed and the air-fuel mixture is compressed as the piston moves from bottom dead center to top dead center. During the power stroke, the valves remain closed and the air-fuel mixture is ignited. The burning mixture causes pressure to rapidly increase, forcing the piston from top dead center to bottom dead center. This thrust downward is the force that rotates the crankshaft. On the exhaust stroke, the exhaust valve is open and the piston moves from bottom dead center to top dead center, pushing the exhaust gases out through the exhaust valve and into the exhaust manifold. This is the complete combined intake, compression, power, and exhaust stroke that repeats or cycles over and over again to make an engine run. Now that we have looked at the basic four-stroke cycle, we are going to go into detail on what happens during each stroke. On the intake stroke, the driver operates the throttle that regulates the air drawn into the combustion chamber. The wider the throttle opening, the more air enters the combustion chamber. The piston traveling down makes a larger area inside the combustion chamber, reducing the pressure on that side of the throttle. The throttle is what determines the difference of pressure on the combustion chamber side of the throttle plate and the atmosphere side of the throttle plate. The most vacuum or largest difference in pressure is at idle, and the least vacuum or pressure difference is at wide open throttle. The pressure moving the air-fuel mixture into the combustion chamber is less than the pressure moving the exhaust out. This means that the intake valve needs to be larger than the exhaust valve to get the needed volume of air into the combustion chamber during the intake stroke. The term ported vacuum refers to pressure that is controlled by throttle movement. As the throttle opens, the throttle plate moves past the port, changing it from the atmosphere side to the manifold side of the throttle plate. The resulting pressure drop is called ported vacuum. As the air is moving into the combustion chamber, the ECM-PCM opens the injector wide open for a precise amount of time to provide the correct ratio of fuel to air. The length of time the injector is held wide open is defined as injector duration. The longer the injector is held wide open, the more fuel enters the combustion chamber. Injector duration is measured in milliseconds. 1 millisecond equals 1/1000th of a second. What we have drawn in during the intake stroke is the air and fuel that will enable the engine to produce power. Let's take a look at what is in this air and fuel that produces this energy. Air is made up partly of oxygen that is represented chemically as O2. The percentage of oxygen in the air is only 21%. Most of the balance, 78%, is made up of nitrogen that is represented chemically as N. A hydrocarbon is a hydrogen and carbon atom that has bonded together. Fuel is hydrocarbons. In other words, carbon and hydrogen atoms that have combined together. The stoichiometric air-fuel ratio by weight is 14.7 parts of air to 1 part of fuel. This ratio produces a good balance between emissions and fuel economy and engine performance. To summarize, during the intake stroke, the throttle regulates the air drawn in by the manifold vacuum, and the ECM-PCM determines the injector duration for a stoichiometric air-fuel ratio in the combustion chamber. The piston is at bottom dead center at the end of the intake stroke. The compression stroke begins at bottom dead center and the piston compresses the air-fuel mixture as it moves to top dead center. Compression ratio is a mathematical formula that uses the combustion chamber volume at bottom dead center in relationship to the combustion chamber volume at top dead center. In this example, we have 10 times the volume at bottom dead center than we have at top dead center, or a 10-to-1 compression ratio. If we only have 8 times the volume at bottom dead center in relationship to top dead center, we have an 8-to-1 compression ratio. The higher the pressure in the combustion chamber prior to burn, the higher the pressure rise during the burn, generating a greater force on the piston. Upon reaching top dead center, the spark plug produces a strong arc between the spark plug electrodes with enough strength to overcome the high pressure inside the combustion chamber and ignite the air-fuel mixture. This is the only stroke that produces energy or power in the four-stroke cycle. The air-fuel mixture burns quickly and creates pressure due to the generation of hot gases. This force on top of the piston powers it down, turning the crankshaft. So the power during this stroke comes from the heat of combustion. When complete combustion takes place, the hydrocarbon bond is broken and becomes separate hydrogen and carbon molecules. The hydrogen and carbon then bond with the oxygen and form carbon dioxide, represented chemically as CO2, and water, represented chemically as H2O. Incomplete combustion produces gases that cause pollutants. A mixture that does not have enough oxygen is defined as a rich mixture. Here is what takes place when the combustion process produces pollutants. If there is not enough oxygen in the mixture during combustion, some hydrocarbon may stay bonded and leave as unburned fuel. The other result is, instead of having the required 2 oxygen atoms to bond with all the carbon, only 1 is available for some. This produces carbon monoxide, represented chemically as CO. Carbon monoxide and hydrocarbon are both pollutants. If the mixture has too much oxygen, it is defined as a lean air-fuel mixture. A lean mixture causes combustion chamber temperatures to increase and may cause the extra oxygen to bond with the nitrogen. Bonds of 1, 2, 3, or more oxygen atoms to a nitrogen atom can result. This produces oxides of nitrogen represented chemically by NOx. The X represents the possibility that it is 1, 2, 3, or more oxygen atoms attached to the nitrogen. Oxides of nitrogen are also pollutants. We are now at bottom dead center at the end of the power stroke, and now begin the exhaust stroke. As the piston moves up, the exhaust gases are pushed out of the combustion chamber through the open exhaust valve. At top dead center, the exhaust stroke ends and the cycle starts all over again with the intake stroke. So now we have a running engine as it first appeared on the scene more than 100 years ago. As shown, our virtual engine only runs well at 1 speed and would sound something like this. In actuality, the valves do not open exactly at the beginning of a stroke, nor close at exactly the end of the stroke. On the intake stroke, the intake valve is kept open past bottom dead center for a few degrees of crankshaft rotation. Inertia is the principle behind the valve staying open. In this case, inertia is the air staying in uniform motion in the same straight line until acted upon by the piston traveling up. The intake valve closes just before the air would stop moving, allowing the maximum charge of air to move into the combustion chamber. On the compression stroke, the air-fuel mixture is ignited before the piston reaches top dead center. This is called spark advance. This happens because it takes a few degrees of crankshaft rotation for the air-fuel mixture to develop the pressure needed to thrust the piston down. To get the most power out of the engine, the pressure from igniting the air-fuel mixture needs to be available just as the piston starts down on the power stroke. The higher the RPM, the more advanced the spark timing needs to be. A few degrees before the end of the power stroke, the exhaust valve opens. This happens to take advantage of the pressure and inertia creating during the power stroke to get the exhaust gases moving out through the exhaust valve. On the exhaust stroke, The intake valve opens before the piston reaches top dead center. Notice the exhaust valve does not close until the intake stroke just begins. This is defined as valve overlap, since both intake and exhaust valves are open at the same time. As the exhaust goes through the open exhaust valve, a low pressure is created, which helps draw in the fresh intake charge, and the air coming in through the intake valve helps push the last of the exhaust gases out. This also has the intake valve open as the piston starts down, getting maximum flow during the intake stroke. The speed of the engine and the resulting speed of the air being drawn in changes what would otherwise be ideal valve opening and closing times. For example, an engine at 600 RPM is turning 10 revolutions per second, the piston is moving 20 strokes per second, and 5 cycles are taking place per second. At 6,000 RPM, everything is 10 times those numbers. As you can see, the amount of time the engine spends on any single stroke is very small. In order to make these events happen when they should, we need to alter valve opening and closing times from basic values. Honda's VTEC system optimizes low and high-speed operation by changing how long a valve is open, while the iVTEC system additionally varies when the valve opens and closes. These dynamics are used on the high-revving, high-performance engines you work on today.